Hi everyone, my name is Martin O'Reilly. I'm Director of Research Engineering at the Alan Turing Institute, and among other things I co-lead a set of projects funded by DARE around getting TREs working on supercomputers, and Fridge is the sort of main backbone for that, so I'll pick everything off that. This is a collaboration with Turing, UCL, University of Bristol and Cambridge as the two air sites, and more recently King's College London and UK Biobank. So I'm going to talk about three things. I'm going to talk a little about what Fridge is, how we're sort of putting Fridge into practice, and a little bit about sort of beyond Fridge, some things that it doesn't, where its limits are, but where there might be some solutions to that. So Fridge is, in essence, a trusted research environment capability for supercomputers, but one that supports the extension of existing information governance from a TRE to the supercomputer. And we need it because TREs generally aren't supercomputers, and supercomputers generally aren't TREs, and establishing trust and governance kind of costs between systems is hard, even when both of those systems are TREs, and this is kind of the whole reason for being for the DARE program. So how does it work? Well, there's sort of two broad ways you can get a TRE on a supercomputer. You can deploy a standalone TRE onto that supercomputer and have it managed there by either the supercomputer providers or someone else, or you can extend one or more existing TREs onto a sort of secure satellite segment deployed on the supercomputer, and that's the approach we've been mostly focusing on in the Fridge world. With this model, the satellite TRE model, we're putting that information governance problem sort of front and center, and we're extending the existing governance from the TRE onto a portion of the supercomputer. And this is adapting and extending the shared responsibility model that many of us are sort of comfortable with the big hyperscalers. Lots of TREs, including many of the NHS secure data environments, are running on sort of one of the big clouds, including Turing's TRE. So let's drill a little bit into how it works. I won't get into sort of the weeds, but fundamentally, it's Fridge allows a subset of the computers in the supercomputer to be temporarily isolated and given under the governance control of a TRE, and in principle should allow different bits of the supercomputer to be put under different TREs, different governance controls at the same time, while still letting the rest of the computer be more fluidly used for non-sensitive work. So it's a combination of things. It's a set of technical protections to help isolate those groups of supercomputers, some of which are discharged by the host, supercomputer host, and some of which are sort of managed by the TRE operator. It allows these groups of supercomputers to be sort of managed by the TRE owner, and that's what brings them into the governance regime. And then the key thing is we're trying to get to a common sort of list of things that the supercomputer owner needs to do to ensure security, and a nice way for that to sort of come back through how they do that's underpinned by their existing sort of information security governance and auditing as the sort of backbone. I'm going to walk you through a kind of step-by-step sort of cartoon process of how that works. So we've got an existing TRE, so that's maybe at Turing, maybe at KCL, King's College, and then the supercomputer at the moment either at Bristol or Cambridge. And the first thing is that the supercomputer admins carve off a secure tenancy, and those computers are now no longer able to talk to the internet or any of the rest of the supercomputer. They then hand that over to that tenancy over to the TRE operator, who deploys all the TRE governance. And in this case, it's a kind of minimal set of things to get a kind of workload manager running, manage some secure persistent storage out to the network, and then we connect those two elements together, and now all of the blue computers can talk, they're in the TRE, the same TRE, they can only talk to each other, and they can't talk to the internet or the rest of the systems around them. So just going one level down, this is the sort of technical separation of concerns. So on the left, you've got the home TRE, so Turing's existing TRE or the King's College London TRE. On the right, you've got one of the air systems, so Isambard AI or Dawn. And the stuff in purple is the stuff that the supercomputer operators need to do. So they set up the tenancy, original tenancy configuration. They put a little wall around it, so that even if we as TRE operators mess everything up, they're still kind of a secure sort of element. But then they stay out of that and they don't look in. And then the other thing is they provide some shared storage, but we sort of manage the encryption. So the bits in green and blue are sort of managed by the TRE operator. So we'll deploy the fridge components in, so that tenancy will have, as well as the secure boundary, we'll have a Kubernetes sort of cluster running in it with a certain set of capabilities. We'll deploy some components that will do workload management, allow upload and download of data, allow containers to be sort of brought into the environment, and manage the kind of transparent encryption if we ever sort of move stuff out of that tenancy. And then the supercomputer operator, sort of the other thing they provide is sort of lifecycle management for the tenancy. When that tenancy gets folded out, all of that, we have high confidence that that data is being sort of zeroed out, and any data that goes out into the persistent storage is under TRE managed keys. And then from the researcher's perspective, they're in their virtual desktop playing with data in the home TRE, and they get to send jobs to the supercomputer to run on the GPUs, and they get to upload data and download data. Well, up to sort of now, or maybe next month, we're at the point of proving out the prototypes, and we've got a pretty good kind of one that's sort of ready to go on Cambridge's system, and we've got a governance workshop on Monday to try and shape through sort of what a version 0.1 can we get our first workload running looks like, and Bristol are not far behind. So we're going to have this running as a proof of concept on both systems, and we're hopefully by the end of this month, next month, going to have had our first low risk workload, but real world workload. But we want to kind of figure out how to make this sort of work at scale, how to make this work for other people. And so we've been funded by DARE to do a real world exemplar sort of follow-on project where we're partnering with King's and some of the data sets that they host and UK Biobank. And the goal here is to figure out how to get some of these large-scale health data sets working on the Air supercomputers. And we want to show that this can be done for 3 somewhat different data sets, each of which has a real-world project running on the supercomputers by the end of the year, by which I mean March 2027. And then while we're not promising to kind of build the production service and scale it, we do want to solve the problem of how does that scale? How do we go from these data sets to other data sets like them? How do we go from one project to all the projects and all the users for those data sets? And crucially, as we're doing this, how do other people who aren't using either Air or one of our TREs pick up the model and use it in their spaces? And the NHS-SD-Network are quite keen to be part of that. So the 3 data sets we're working with are UK Biobank, which is the large sort of consented 500,000 subject longitudinal research cohort, got lots of sort of multimodal data and has been running for some time. So we've got recently the GP sort of primary and secondary care data coming in. Pharos AI is similarly a large scale multimodal data set, lots of patients, lots of linked data, lots of sample points. And the AI Centre for Values-Based Healthcare, we're taking a subset of their data, which is a large number of brain MRI images associated with metadata and the clinical radiology reports. And the commonality here that makes them interesting for sort of AI supercomputer-focused project is they're large-scale multimodal health data sets. There's a large imaging component, so they're hard to do on smaller GPU systems, and they've all got lots of projects that want to apply AI tools to it, and they're kind of straining at the seams of the TREs they've got access to at the moment. So the key challenges as we go from proof of concept to really validating this in a full real-world context are how do we go from user uploads data as part of a project to that data exists on the Air data store, as Sadaf was talking about earlier, that we can securely host that, update it sensibly, that we can enforce the data providers access control so that the projects that have access to a subset of the data will only see that subset of the single copy on Air. How do we integrate into DSIT's allocation process for Air? So Sadaf showed a sort of picture of how to get the general picture of data providers involved in that, but there's also the question of sort of how does the sort of governance and liability sort of threads that sort of go through the existing allocation process sort of work for these sorts of data sets where DSIT, Bristol or Cambridge and the data provider all have their own interests and their own sort of worries about sort of liability and how data is controlled. How do we provide an easy pathway for TREs that aren't Turing or KCL to connect to AIR? How do we provide options for researchers who don't have home TRE, but would still like to use these data sets on AIR? How do we make it so that instead of one project, we can have hundreds of projects and thousands of researchers reach those data sets? And then sort of finally, how can this work in other contexts? Like, so with the NHS-network, they've got these SDEs that are starting to figure out the governance challenges of pooling data together in a sort of more granular way than's available nationally. But within those SDEs, they don't have the supercomputing capability. But within those partnerships, they've got lots of universities that do. So they've got the same sort of challenge. They need to go outside of their governance boundary. So they're interested in this idea of pushing that governance boundary out onto somebody else's computer. And then the last thing I want to talk about is sort of the limits of Fridge and some thoughts and research we're doing to sort of figure out kind of what might help with that. So the big thing to remember with Fridge is it's sort of still the shared responsibility model. So the supercomputer host has put that green box around, which means even if we mess up all the blue things, if they've done their job right, there's a safety net. But even though they've said and signed an agreement to say they won't look inside, they can still choose to look inside if they want to. And so this shared responsibility model might not be sufficient for some of the higher sensitivity data sets or data providers. It doesn't support this long tail. There's a lot of AI compute out there on the people's desks or in a lab cupboard. That's sufficient for the jobs at hand, but the data that they want to access is sensitive. And even though it's only one box with a number of GPUs in it, that's prohibitively expensive or difficult to secure on the sort of home TRE for that data set. So if you're thinking about this as a space of sort of scale and isolation of the computer system and sensitivity or risk of the data, you've got the green bit we've all kind of got comfortable with over the last 5 years or so of running new TREs on the cloud. With Fridge, we're pulling that sort of shared responsibility model leftwards to national and institutional kind of provided sort of well set up HPC providers. But to go beyond that, we're going to need to do something different. So what we're looking at is confidential computing. So we're all familiar with data encrypted at rest. If my laptop gets stolen or my phone gets stolen, then that, as soon as it gets turned off, the data's encrypted. You can't pull the hard drive or pull the memory and expect to get the results without doing something quite clever. And when we connect to the banks or we VPN into our home universities or we SSH to one of the supercomputers, that data is being encrypted in transit. And so what confidential computing does is there's some capabilities in modern hardware. So most modern CPUs and some modern GPUs that will allow you to securely establish and verify a confidential virtual machine that the low-level sort of metal, from the processor provider, will guarantee cannot be seen by the organization that physically holds and is root on the bare metal. There's two ways we can kind of use that. One is for the big supercomputers and one is for the long tail. So for the big supercomputers, we can run confidential virtual machines or confidential containers inside the TREs and only send encrypted data and only inject the keys into those confidential VMs. And then even if the supercomputer host breaks that agreement and peeks inside the green box, they can't see anything. And so let's go up the risk scale. It would say that for cloud providers and large-scale HPC providers, we can maybe deal with more sensitive data because we no longer have to rely on them to do their bit. We still want that green box because we don't fully trust ourselves to do our bit against all future attacks. So we'd like, if the blue bit fails, the green bit perimeters to still be there. But the other thing we can think about is, does this give us an option bringing in that long tail, smaller scale machines that are either hosted by individual researchers or individual labs? So we can do the same thing. We can configure them as a confidential VM if they're prepared to let us do that. We can set up a secure tunnel, but we're sort of missing the green box. So, and the nature of this is we can't sort of trust these folk in general to be competent enough, and we can't go and audit and the large number of them to be confident that green box will be there. So if we mess up with the blue box and we allow a kind of route out to the internet, then we've lost one of those onion layers. And so it's a part of what we have to, and so while this gives us the option kind of go down that scale and isolation route to these sort of lower scale systems, we've deliberately coloured it red. It's a thing for us to figure out whether that is enough or whether there's other things that we can do that kind of give us that sort of multiple independent things have to go wrong before we get an external or lateral data breach. And so, what are we doing sort of to figure that out? Well, the goal here is to define a bring your own compute model for TREs. We don't know if that goal is achievable, but that's part of what makes it a more next generation kind of research project rather than how do we bring something to implementation. But the things we're looking to do are evaluate the confidential compute capabilities of these current GPUs and CPUs. So the most recent generations of Intel, AMD, and ARM all have this capability. With ARM, it depends, I guess, on whether the individual chip manufacturer has adopted the extensions. But for example, the next generation of sort of the Vera Rubin generation of ARM NVIDIA kind of super chip will support that. The current GH sort of doesn't, but from Hopper, through Blackwell, the individual NVIDIA GPUs do when paired with a CPU that supports it. So we're playing with some of those in the cloud, and we're working with people in this community to sort of play with some of these in a supercomputer context. And that would be one of my calls for action for you at the end, is if you've got some of these systems where you've got a modern Intel or AMD processor, a Hopper or a Blackwell, a discrete NVIDIA GPU, we would like to talk to you. We're going to sort of, beyond how easy are these things to configure in a reliable way, in a safe way, in a way that we can be confident we haven't sort of accidentally missed something. We're going to try and validate these inside that TRE context. So what does it mean to sort of wrap that governance barrier around these, either in the supercomputer context or in the under the desk or in the cupboard context? And as we are with Fridge, we're going to share the coding guidance that we're sort of generating. The thing we might share at the end is, do not do this in reality. It's not ready yet. Or it might be like it works great for supercomputers with a green box. It's not quite enough on its own unless it's really, really sort of low sensitive data. So how can you get involved? If you're a data provider, we'd love to talk to you about whether this sort of model works for your information governance context, and sort of really sort of test that. So with UK Biobank, we're going through their certified TRE process, both for our TRE as it stands and for the combined supercomputer plus cloud TRE sort of Fridge. If you're a TRE provider, can you support this satellite model? Like, would you be comfortable doing your bit to kind of take responsibility for a secure tenancy on someone else's computer and deploy the bits you need to deploy? If you're a supercomputer provider, can you support this model of providing this secure tenancy, handing it over, promising to do your bit, binding that back to your kind of ISO audits or CAF? Just that last question again, if you have confidential computing enabled CPUs and GPUs, we would love to talk to you, because there's not many of the current sort of a generation of large scale GPU clusters that are set up like that at the moment. And I think that's me done. So if you want to get involved, drop us a line. We can have a one-to-one chat. We're looking to have some workshops over this calendar year. Or once we've got it working and on Dawn and Isambard, you're very free to take Fridge and take it for a ride on your own TRE supercomputer pairing.